Now, when it comes to acid-base reactions, according to the Bronsted-Lowry theory, a proton transfer doesn't always readily happen. In fact, there are many cases where the two substances are mixed together, and despite an acid and a base being present, a proton transfer doesn't actually happen. When it doesn't happen, or doesn't happen effectively, or only partially occurs, we say that the reactants are favored, or that the equilibrium position has shifted left. In other words, what we're really saying is that this reaction is not spontaneous. So when it comes to acid-base reactions, when a reaction doesn't occur, then we just say that the reaction shifts left and it has a really, really low percent yields. So there's a couple of terms that are going to be synonymous with each other. Shifts left is synonymous with reactants being favored, and now reactants being favored is synonymous with a very low percent yield, and a very low percent yield is synonymous with the reaction is non-spontaneous. And so when we have a reaction that is non-spontaneous, or the reactants are favored in an acid-base reaction, we wouldn't expect to see the normal signs of that a chemical change is occurring, like bubbles, heat, change in pH, etc., etc., etc. Now, if the reaction does work, and you mix two substances together in a lab, and you see that there's bubbles forming or heat produced, a change in pH, etc., then you can reasonably say that the products are favored, or that the forward reaction is being favored in terms of equilibrium. And when that happens, we say that terms like shifts right, products favored, and spontaneous are in fact synonymous. And so from now on, when an acid-base reaction actually creates a neutralization reaction, meaning they do react together and the pH changes, we're going to say that the reaction is spontaneous, or that the products are favored. So what we have here is the 5 steps that you could use to help you determine whether your reactants or products will be favored once an acid is introduced with a base and vice versa. The first thing that we're going to do is we're going to list all entities present. That means that we're always going to split strong acids, strong bases, and ionic compounds into ions. And remember, ions have a positive and negative charge. Once we have all our ions listed, then we're going to identify all the acids and bases using the data booklet. Remember that the left side refers to the acids, and the right side refers to the bases. Now, once we have that, we're going to use, similar to what we did in spontaneity, the concept of comparing the strength of acids and strength of bases to each other. And so the strongest acid, kind of like the strongest oxidizing agent in our reduction potential table, is always going to be at the top left. So whichever one is the highest on the left side is the strongest acid, while the strongest base is going to be towards the bottom right. So the lower on the right side of the chart your base is, the stronger it is. Then we assess the equilibrium position. And it's similar to spontaneity, where we see if the oxidizing agent is above the reducing agent. This time, we're going to see if the strongest acid of all the entities is above the strongest base. And if that's the case, then the reaction is spontaneous, the products are favored, and you would actually see some sort of signs of neutralization taking place. And these would be signs like odor, so it should smell, a change in smell perhaps, pH should change, and you would indicate that using chemical indicators like phenolphthalein and bromothymol blue, and as well there'd be bubbles of some sort. Now, one thing that is worth mentioning is that if the reverse happens, so your strongest base is above your strongest acid, then reactants are favored, of course. And any of those, signs of a neutralization reaction that we saw would not be present. Now, the fifth and final step of this process, and it won't always be asked of you, but it's good to get in the habit of, is if we ask you to write the predominant reaction, okay, between the strongest acid and the strongest base, most of the time if we ask you to do this, it would be spontaneous. But in the event that it's not, what we do is we react, okay, the strongest acid with the strongest base. And that reaction should be written in the form of a Bronsted-Lowry reaction where we show, right, the transfer of one proton from the strong acid to the strong base. Okay, and I can't stress enough that I want you only to show one proton. So, with our first example here, it says, what will be the predominant reaction if spilled drain cleaner sodium hydroxide solution is neutralized with vinegar acid? So, first thing, vinegar refers to acetic acid. So vinegar, okay, and we'll just we'll write that a little bit neater here. Vinegar is the same thing as acetic acid, which in our data booklet is CH3COOH. Okay, our reactants are products favorites. So the first thing we're going to do is going to list all the ions, and we're not going to split apart any weak acids or bases. So we're going to go CH3COOH. This is weak, so we're not going to split. So we're going to write don't split. We have Na plus, we have OH minus, and of course there's water since these are in solution. The next thing that we're going to do is looking in our data booklet on pages 8 and 9. We're going to determine which one of these are acids and bases. And so for step 2, our acids are going to be in red and our bases are going to be in blue. And so here is an acid. This is also an acid. H2O is a base, hydroxide is a base, and Na plus is not there, so it's a spectator ion. Now the third part is we're going to find the strongest acid and the strongest base. The strongest acid is going to be the one that's closest to the top left, and the strongest base is going to be the one that is closest to the bottom right. So using this in the data booklet, which yours looks very, very similar to here, remember that it is worth noting that the strongest acid is at the top and then it decreases in acid strength as we go towards the bottom, whereas the base, the strongest base, is towards the bottom and it decreases in strength as we go to the top. So what we're going to do is we're going to locate our ethanoic acid right here, which is acetic acid. It's the same thing. And that's our strongest acid. And we're going to go find an OH ion, to which we could see it's right here. And so what we could see is that the strongest acid is definitely above the strongest base. That would make our acetic acid the strongest acid and our base the strongest base. And as we would have now seen, acetic acid is above OH minus, which this is the strongest acid and this is the strongest base. And so it is above, and so we're going to say that because of this, products are favored. Okay, so now the last part here, we're going to write the reaction between the strongest acid and the strongest base. And so it'll look like this. We're going to write CH3, so this was step 4 here. Step 5, CH3COOH plus OH minus. This one is going to give one proton over here, so it becomes CH3COO minus plus H2O. This one gained a proton. Notice this change in charges. This is kind of what we were talking about last time. And so here is your final forward reaction of what we can expect to happen when we react acetic acid with sodium hydroxide. Okay, so for the second example here, it says ammonium nitrate fertilizer is produced by the quantitative reaction of aqueous ammonia with nitric acid. Write a Bronsted-Lowry reaction and prove that the reaction shifts right. So we tell you that there's a reaction. That's how we know it shifts right. So our products, our reactants first and foremost, we're going to list them first. It's NH3 gas, solution, so aqueous. And it's nitric acid. Now remember, nitric acid is a strong acid, so it's going to fully ionize into H plus and NO3 minus. So we're going to write NO3 minus and H plus. And we're going to include water because it is a solution. Next, what we do is in red, I'm going to identify all the acids, and in blue, we're going to identify the bases. And so looking at our data booklet on page 8 and 9, that's a base. This is a base. And this is an acid. Remember that this is really short for H3O plus. And water is an acid and a base. Okay. So we have that. Now what we're going to do is, using the data booklet, we're going to identify the strongest acid and the strongest base. And so the strongest acid, the one that was closest to the top, was your hydronium ion, which is H3O plus. And the strongest base would be NH3. Now, from the fourth step, we're going to go right to the data booklet and see if this reaction is going to be spontaneous, or if the products will be favored, or if it'll shift right. These are all synonyms. So let's take a look at the data booklet. For the second question, we realize that the hydronium ion was the strongest acid. And then we also saw that ammonia, NH3, was the strongest base, and it's right over here. So much like in our previous question, we can see that clearly the strongest acid is above the strongest base. So by now, we should have seen that indeed your H3O plus, which was your SA, your strong acid, was above NH3, which was the strongest base. So this one is going to have products favored, just like we had anticipated. And so the last thing that we're going to do, which is really what it wants us to do, is we're going to create that reaction. So we're going to roll up. Now it says it's a quantitative reaction, which means that you're only going to do a single arrow. So we have H3O plus plus NH3, which gives us, since this will donate a hydrogen to the base, it'll become H2O plus NH4 plus. And this is our final solution. Of course, I'm going to include the states, because states do matter in chemistry. And one last thing that I want to point out is that this refers to the ammonium nitrate. But of course, we didn't list the nitrate because it was a spectator ion. Okay? right, so to test out our theory, what we're going to do is we're going to combine acetic acid. I'm going to dilute this, of course, to make an aqueous solution with sodium carbonate. And again, this is going to be diluted, turned into aqueous, so that we can use the actual ions. And using our methods of predictability, let's see if the predicted reaction would take place. So here's our final finished solution after the reaction. We saw that the indicator turned from pink to colorless, which means that the pH changed, which means that the products were favored in this reaction. So acetic acid, which when we look in our data booklet is the strongest acid listed amongst all the entities there, when reacted with the carbonate ion, CO3 2-, it should indeed be spontaneous. And when you look at the work that's done at the corner of the screen here, you would see that, well, predictably so, there was a forward reaction, the products were favored, and that was evidenced by our the change in indicator color. So what this reaction produced was a conjugate acid of the hydrogen carbonate ion, and of course the conjugate base was the acetate ion or the ethanoate ion. Both of them are listed in your data booklet. So it looks like what we're doing on pen and paper actually works in the real world, and we were able to effectively neutralize or produce a forward reaction between an acid that was above the strongest base.